of MEB 1012, Introduction to Material Science. Right. Alhamdulillahirabbil alamin wassalatu wassalamu ala asyrafil anbiya wal mursalin wa ala alihi wa sahbihi ajmain. Rabbi shrah li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Allahumma Rabbana atina min ladunka rahmah wa hayyi' lana min amrina rasyada. Rabbi yassir wa la tu'assir wa tammim bil khair. Wala hawla wala quwwata illa billahil aliyyil azim. Okay. Let's recite Al-Fatihah before we continue. A'udzu billahi minasyaitonir rajim. Bismillahirrahmanirrahim. Alhamdulillahirabbil alamin. Ar-Rahmanir-Rahim. Maliki yaumiddin. Iyyaka na'budu wa iyyaka nasta'in. Ihdinas siratal mustaqim, siratal ladzina an'amta 'alaihim ghairil maghdubi 'alaihim waladdallin. Amin. All right. So I suppose you can see my slide. All right. So there's no issue with our. Please undo your drawing. Yeah. All right. To be responsible students, to be kind students. Please do not meddle around with the slide. For some reason, you can write on it. So just just be good and not interfere with my annotation, because otherwise I cannot teach you. All right. So I hope you just stay put and just put on your ears. Alhamdulillah, today is actually week 12. I'm just so glad that things are moving towards the end. All right. Yeah, we have been, discussing about things. We have talked about lots of materials related matters. So hopefully you already gain lots of knowledge, upgraded your knowledge about materials, what you never known before. Now you are better informed, and hopefully you can, apply from this course to the future courses. And of course, when you start working in the industry or wherever you work, hopefully the knowledge becomes useful. And then that can be my amal jariyah, inshallah, hopefully. Okay, put the knowledge to good use, then I can get a fair share of that knowledge then. Right, so syukur, alhamdulillah, for what we have gone through, the ups and downs with the online issue. But, we have to survive. We have to go through this phase. Very challenging, not only on your side, it's more challenging on the instructor side. So I wish you all the best for your future courses, and we are still uncertain how the October or September semester is going to proceed. As it is now, the planning is that some courses with large number of students will go for online, and the smaller sized group will go for face-to-face. So you cannot avoid it. I think at least for this year, we still have to work through the online lecture. I know it's not the most effective, under the current situation, under the whatever disadvantage that we have, but you as the learner will have to be more responsible for your own learning. I already got my degree, you are working for your degree. So you have to work more. You have to put more effort. You have to be more responsible when we do online learning. I know sometimes you are just lost in the middle. You just leave your laptop alone, you are not there, but you are logged in. So those are not the very responsible attitude. So if you really want to learn, you don't want to miss out, during this MCO, EMCO, whatever phase, you have to be responsible yourself. I know dealing with first year, this is your first year. Sometimes you are not used to the way of undergraduate, how it works. But you better quickly learn, all right? You have to be matured. like playing on the screen is not a mature attitude, right? It doesn't reflect that you are responsible. So, must always practice good ethics, good behavior, because akhlaq is, what we are supposed to work on. We have to be make sure our akhlaq is the tip top, the best. Then only we will be safe, dunya and akhirat. All right. Okay. So, any feedback to me before we proceed? Anything that you want to ask? Because this is our last class. I'm hoping to finish before Zohor, if not sooner. All right. Because this is one last topic to be covered. Yes, it is going to be covered in your EA, extended assignment. A little bit information on your EA. EA is going to be like 1st September, I think. 1st September for you. And then we're going to have 2 questions on EA. So big questions. One is 50 marks. So hopefully you really put your effort and time to answer them all very carefully. So you should have some guideline in your mind. If it is 50 marks, make sure you have 50 points. 50 good points, so to ensure that you're gonna have the full marks. Sometimes you just don't think about the marks. If we put 10 marks, you just put one answer, one line answer, that couldn't worth 10 marks, right? So it has to be strategic when you answer the EA. That EA is going to be 40%. Jadi don't play. Yeah? You need to really prepare for your EA. Alright, so when EA 1 September. Okay, kalau macam tu, let's proceed. I'm gonna show a bigger screen on my computer. Therefore, I will not be able to see the chat. Alright, so you have to alert me if anything went wrong. If you have any question, just put on your mic. And I really wish that everybody to show your face on this last day, so that we can take a picture, all right? Then record that as a history, having first virtual, IMS class. So I hope you are ready to put on your tudung or, put on your whatever to be presentable and show your face. Open up your video or webcam and we can have a snapshot of everybody online. So I hope I can get your cooperation there. All right. So whenever you're ready, you can just show on your webcam. All right. Okay. So this is a bit weird having a online class. We have never interacted personally, right? So there's no personal touch between you students and the instructors, all right? Anyway, on this last class, I wish to show my face so that when you bump into me sometime, you know that I have been your lecturer once, all right? Okay, let's begin, 12:11. Don't forget to sign in into your Power Apps, all right? And then later you can answer the poll as usual. All right. Okay. So the last class. So don't disappoint me. Right. Okay. Today, what is our topic? Yeah. Okay. Our topic. Okay. Today, the learning outcomes. All right. There will be like basically three. Nak sebut tiga kot. 3 of them. We're gonna learn about microstructures. Okay. Before. You may have seen alpha, you may have seen austenite, apa lagi you ada pearlite. Okay, that's what we have heard before. All right, but today we're gonna expand our knowledge, boundary of knowledge, and learn about different microstructures. Now we're gonna have fine pearlite and coarse pearlite, satu halus, satu kasar. And then we're going to learn about bainite, okay, sphaerodite. I think you never heard about that before. Then we have martensite, also tempered methanside. So we're going to discover this. Okay, you must be able to describe these microstructures. And then cite general mechanical characteristics of these microconstituents. We call them as microconstituents, okay, because they are a phase, but then they have different microconstituents, all right. So you must be able to explain their behavior in terms of the microstructure or crystal structure. And then this is the big thing, okay, given the isothermal transformation diagram is quite a mouthful to mention. So isothermal transformation, or short form dia ialah TTT. What does TTT stands for? T is for time, temperature, transformation diagram. Okay, so sometimes we call it isothermal transformation, sometimes we call it TTT. For some iron carbon alloy, you need to be able to design a heat treatment that will produce a specified microstructure. This is your aim. This is your task to be able to do at the end of the lecture today. Okay, to design a heat treatment to produce certain microstructure. How difficult could that be? No, it's not going to be difficult. Okay, but you have to pay attention. All right, where do we begin? You know, it's always about where we are coming from and where we're going to, right? So here, we start actually with phase diagram. Okay, this is where we are actually. We know something about phase diagram. We learned this before, last chapter. Okay, and you need to know that, okay, phase diagram is actually under equilibrium conditions. What does that mean? Equilibrium means nothing changes in time, all right? So no changes in phase development, no phase transformation over time. Everything is dead already. I mean, everything is stable. Okay, that's what we call under equilibrium. So phase diagram is something like this, all right? This is actually reflecting the phases that are present under equilibrium condition. So to reach equilibrium condition is not easy, and it's not actually practical in the normal situation in the industry or our daily life. All right. Therefore, there's something missing about this phase diagram. The factor of time, right? Because time is constant kat sini, right? Nothing is changes over time. So we need to develop a diagram that will allow us to work beyond equilibrium. I mean, not when it is equilibrium, because to reach equilibrium it's very long time. Therefore, it may not be practical. So engineers, material scientists, you know, they come up with another diagram that will tell you about the phases that's going to be present. There are still phases, but then with the factor of time. Okay, so this is called time, temperature, transformation diagram or plot, right? So that's why TTTT. So we move from phase diagram, equilibrium, into something that has time factor in it, right? And but this time when it is time, temperature, transformation, the time is there, but now the transformation that happens here is actually but it happened at isothermal. So what is isothermal? Okay, anybody know what is isothermal? Kau ada boleh jawab kat sini? Okay, I'm looking at the chat now. If we know what is isothermal, anybody want to say? You can just type what is isothermal. No? No idea what is isothermal? Okay, temperature remains constant, correct. All right, so in an isothermal transformation, all right, you hold the temperature constant. So you can imagine that like here, okay, in this diagram, this is fraction transformation, I mean how much your new phase is forming, and then this is actually time. So what happened is that initially nothing happened. You need to give some time for nucleation to happen. So this phase here is nucleation. You need to form small nucleus before a new big phase come up. Right? It all starts from a small matter. So that nucleation will happen over time, and then it starts to pick up. Then now I'm going to have phase transformation, growing a lot more until I reach 1. That means 100% transformation. All right. So this one happened at one particular temperature. So this is at T1. All right. So we monitor the fraction transformation of the phase. Okay. We jot down when it starts, when it reaches the 50% point. This is 50% transformation line. Yeah, that's cantik. Okay, 50%. And over here, you reach 100%. All right. So you do this for all temperatures. For example, here they show 135 degrees, 119, 30, many different temperatures. Each one is happening at isothermal temperature. So one constant temperature. So you maintain your temperature and then you observe nucleation happening, and then you start to grow your nucleus into a phase, and then let that phase grow until to completion. So that is what isothermal transformation is all about. So finally, engineers come up with this diagram from this single phase transformation diagram. Okay, so that is in just to introduce you where we are coming from and where we're going to. So this is the diagram we're going to work in chapter 10. All right, any question? Anything that you want to ask at this point? Okay, so kalau nak tanya, you can write. I'm waiting for your question just to clear things before we move. Clear for now? Okay, good. All right, so now let's move to the next slide. Okay, I'll try to be fast. Okay, so this is again the plot that I showed you earlier. Okay, this is what we call phase transformation ataupun rate of reaction. All right, so this is fraction transform. How much? So in terms of fraction, so it's 0 to 1. Okay, ini adalah fraction. Fraction adalah from 0 to 1. I can convert this into percentage lah, 0 to 100%. So as I said just now, initially you don't see anything because nucleation is happening. No new phase is coming up. This fase is just like human being lah. Okay, when we come to the world, we didn't start off like a big baby, you know. We start off as a drop of liquid and then develop into blood and then develop into flesh and so forth, right? So this is the same thing happening to phases. Okay, it started with nucleation and then it starts to grow. So this is where you start to have your new phase to coming up. Here is the midpoint where you have 50% conversion, and then at this point it's 100% conversion. So your rate of transformation, rate is over time lah, yeah. When we call rate, that means it's over time. So the rate is actually the slope of this curve at 50% conversion. That is how we define rate of transformation. And this is following Avrami rate equation, where fraction transform y equals to 1. We started, we expect, you know, 1 minus exponential minus kt to the power of n. So this is how you calculate amount of new phase coming out. By convention, rate of reaction is the inverse of the time required to reach 50% conversion, 50% rate of transformation. So that is the rate of transformation. Okay, and we already deliberated on this curve. All right, this S curve. We normally call this as S curve. All right. In this example, this is a different system. As you increase the temperature, you are shortening your nucleation time, and then you are also increasing your rate of transformation. So the temperature has influence on the rate of transformation. So the rate of transformation, I said just now, is the inverse of time for the system to reach 50%. That's why they tanda 0.5. Okay, the time required to reach that point, this time T 0.5, masuk dalam equation, you got rate of reaction, which is actually equals to a constant multiply with E minus Q over RT, our typical Arrhenius equation. You have seen Arrhenius equation before when we talk about diffusion and when we talk about vacancy. All right, because these two, they are temperature dependent processes. So all temperature dependent processes is governed by Arrhenius expression like this. All right, so that one shouldn't be a problem. Okay, good. Okay, just storytelling. Okay, now let's look at eutectoid. You must know what eutectoid transformation is all about. Okay, if you don't remember, when we talk about eutectoid, our system is iron carbon. Don't forget, must know that. Okay, eutectoid is referring to the iron carbon phase diagram. And eutectoid transformation is referring to the conversion of gamma, where it converts into alpha and cementite. Okay, tak erti tulis kecil. Alright. Alright, so that is eutectoid transformation, which happens at 7 to 7. 7 to 7. I'm sure you have learned this in phase diagram. You studied this for your exam that day. Okay, so what actually happened during that eutectoid transformation? You are converting your austenite into layers of alpha and cementite, alpha and cementite. So these alternating layers or lamella is what we call pearlite. Okay, no, nothing new. It's what we discovered in chapter 9. So this thing will just grow over time. You hold the temperature and then it will just consume this austenite, change into alpha and cementite in alternating layers. So what happens is that your carbon will move, okay? Carbon will travel to go into the alpha layer and to the cementite layer, right? So what's important to note here is that, okay, in this plot, you see that 600 degrees transformation curve, and then 650, 675. So in this case, what you see is that the higher the temperature, okay, the S-curve is shifted to longer times. That means the nucleation will take more time to happen before growth starts, all right? And you can see the rate of reaction, the slope, right, is actually steeper the lower the temperature is. So there are two things here, very important, is delta T. One is the delta T. Delta T referring to what? Delta T is the difference between T eutectoid and your operating temperature. All right? So, of course, you are reducing your temperature. So, TE is the highest temperature. This is your transformation temperature. The bigger the delta H, that means you are lower in the phase diagram. Mana the phase diagram? Kalau phase diagram, just now we have phase diagram like this. Alright, this is T eutectoid. So lower temperature means you are down here. Alright, so 600 maybe just about there. Maybe kat sini lah 600, and then 650, and then 675, you know, there. So delta T is that the change or the difference between your temperature of transformation compared to the eutectoid temperature, right? So in this case, if you are 600, delta T is larger. If you are 675, your delta T is small because it's closer to 7 to 7. I hope you follow me. Okay. So that's one thing, delta T. And then another thing is the T itself. The T itself is ni lah. Okay, this is lower T. This is higher T. The T is higher, but delta T is smaller. Okay, so nucleation rate, how many small nucleus coming up, increases with delta T. The larger the difference in temperature, okay, more nucleus will come up. Okay, that's what it says. Okay, therefore, what happened is that, okay, if you are forming at higher temperature, okay, if you're forming at higher temperature like 675, that means close to the TE here, you're going to have coarse pearlite. If you are forming at lower temperature, you're going to have fine pearlite. What's the difference between the two? Here it tells you what the difference is. If it is coarse, that means the layers are thick, right? You can see the white layers are thick here, and then even the darker lines also, you know, it's actually appearing thicker. And in fine pearlite, all those lines are very fine. So until you can't even really see over here, right? So less white region, thin layers of alpha and cementite is called fine pearlite. So for fine pearlite, the mechanical property becomes harder because it's very fine. So it's resisting deformation better. Okay, compared to a coarse pearlite like this, they are a little bit softer. All right. So you can compare between small grains and big grains lah, in that sense, right? So how do we get coarse and how do we get fine? It depends on the temperature of transformation. Okay, let's move into the next slide. I think we can see here. Okay, so what happened when T is way below TE? This is like 600 degrees just now. Okay, delta T is very big. When delta T is big, your nucleation rate is high. And because temperature is low, your growth rate is low. Therefore, you got lots of nucleus, but they don't grow big because temperature is low. Movement is a bit slow, right? Compared to just temperature just below TE, that means temperature is high, 675. So delta T is small. Over here, that means delta T small because close to TE. Okay, nucleation rate is low because nucleation rate is proportional with delta T. And then because the temperature is high, growth is high. Okay, growth rate is high. Therefore, not many nucleus will come out, but they will grow big. Okay, therefore, you're going to get coarse pearlite in this sense. You're going to get fine pearlite in this sense. And then the tengah-tengah one is moderate lah. Okay, so this is what happening as you isothermally transform it at different temperature. Okay, before we don't talk about different temperature because it's already at equilibrium. So now you realize that you can play around with it. You can transform the pearlite at different temperature, and then depending on the temperature where you are, you're going to get the different microstructure. Okay, so any question? Let's tengok whether do you have any question. Okay, I'm looking at the chat board now. If you have any question, because it can be a bit high level, you know, lots of concept there. So I hope, you know, you can later watch the video to get a repeat of the method. All right, so tengok somebody is typing and see what is the question. TE is eutectoid transformation temperature. All right, so this is eutectoid. TE is this, referring to this temperature. All right, this line 727, that is the eutectoid. Why we are referring to this temperature? Because we are only interested in the transformation of austenite into alpha and cementite. We are interested for the transformation at this point, for this composition. Okay, that is eutectoid composition. This is eutectoid temperature. All right, so we only focus at this composition. I'm not talking about any other composition. Yeah, this particular point here. Itu kena faham. All right, so what happened, because under our isothermal transformation, we are not cooling it slowly for equilibrium, we actually undercool it. So transformation going to take place below 727. That's why we call it undercooling. All right, where transformation is less than 727. Kalau at equilibrium, kalau you phase diagram betul-betul, memang it only happen at 727. But now we cheat the system a little bit, we undercool it, and then things will still transform. All right. So this is the equation of the eutectoid reaction that we are focusing on. This equation you cannot forget. You must know this equation very well. Patutnya dalam phase diagram hari tu you already understand this equation. Those are just composition of the phases present. Alright, okay, let's move on. If that's all the question is. So getting back to this transformation curve, this S curve, we're just going to explain a little bit how we arrive at this TTT diagram looking like a highway. I always call this like a highway lah. All right. So this highway, okay, if I can describe this plot a little bit, this is only telling you the microstructures that are present, okay, over time at particular isothermal transformation. Apa dia A? A is austenite, right? This P is not puteri but it's pearlite. B is bainite, right? M is martensite. So these are all the new microstructures that come up because of the undercooling, because we are transforming at isothermal temperature. We are not doing it at equilibrium. So those non-equilibrium phases coming up now, like bainite and martensite. Okay, so what are the lines? This line actually, if I take this red line, this red line is actually telling you when the austenite starts to change into another phase. If it is in this region, okay, before you're gonna have A, austenite. Once you maintain your temperature, katakanlah you maintain at 700, maintain for certain time, until you hit this point, it tells you that you're gonna start to transform your austenite into pearlite, because this is the region of pearlite. Okay, this is the red line tells you the initial starting point of the transformation. All right, and then if you maintain the temperature further sampai, katalah ni tak nampak kan, until yang tu maybe I cannot show you. Let's say I put my temperature 600. Okay, I maintain my temperature at 600. At that point, my austenite starts to transform to pearlite. That line tells me that time, what time is that? Time tu kena baca down here lah. How long? Oh, about 1 second. So if I hold 600 degrees for 1 second, and then my pearlite will start to appear. Pearlite means alternating layers lah. Okay, don't forget pearlite is alpha and cementite. And then if I keep longer, sampai to this middle point, for that middle point berapa? Maybe dalam 4 second ke 3 second ke? What happened? I got 50% pearlite. So this middle line, this dashed line, is the 50% conversion line. If I hold longer, what happened? If I hold until that point, longer to sampai bila? Sampai 10 second maybe. If I hold until 10 seconds, I'm going to transform 100% from austenite into pearlite, because this green line now is actually the 100% transformation line. Susah ke? Okay, so this PPT diagram basically tells you when transformation starts, when transformation ends. Okay, when to in terms of time lah, because this part C here is time. Alright, in the middle somewhere, ini macam estimate lah. In the middle somewhere where your dotted line is, your dash line is, will tell you 50% conversion. So in this region actually ada dua benda, ada two areas. They are marked with this dash line. Apa benda ni pula? At this temperature, basically 540 kat sini lah, about 540, and never can draw straight line. Okay, at 540, okay, you gonna form pearlite above. Above that temperature, you form pearlite P. Below this temperature, you gonna form bainite. Just a new microconstituent. Alright, so bainite ni dia maybe, okay, bainite the apa tu microstructure mungkin looking a bit different. Dia macam platelet, maybe macam apa dipanggil ni ya, needles or something like that ya. So the microstructure is different. Yang ini lamina kan, is alternating layers. So a new microstructure come up, okay, bainite below 540. Okay. And then what happened here, okay, this is the line where martensite starts to form. If you drive your transformation at 220, this is roughly 200, yeah, about 220, you're going to start to form martensite. Martensite pula, the microstructure is just needles, blades, you know, just panjang-panjang macam tu lah. Okay, and if you draw, you go down further until you reach to this temperature, you're going to form 90% martensite. So anything below that, you're going to form 100% martensite. So martensite ni a bit different than the other microstructures, because if you notice kan, martensite punya transformation curve doesn't follow this curvy curve. Okay, this highway. Martensite nampaknya horizontal line. That means apa? Transformation of martensite depends just on temperature. Alright, there's no diffusion. It does not depend on diffusion. Okay, these two, pearlite and bainite, depends on the movement of atoms, the carbon movement of diffusion lah. Okay, based on diffusion. Tapi martensite tak. Martensite ni just by a jump of carbon atom out of the out of the crystal structure, dia jadi a new phase, and that is martensite. So martensite doesn't actually depends on time, sebab tu dia kata diffusionless. Kalau it is based on diffusion, it requires time. Tapi you tengok for martensite, it only depends on the temperature where you are. If you are at 100 degrees, you're going to have 100% martensite. So it doesn't matter how long you hold that transformation. Faham? Any any question? Let me pause at that point, because okay, ada anything you want to clarify about this TTT diagram? So you can write your question, I can check back your question, but basically, you know, let me remove all this thing. Okay, so then you have this TTT diagram, clean, right, for you to use to design a heat treatment that will give you the right microstructure that you want. So maybe you want 100% pearlite, maybe you want 50% pearlite, you want 50% binet, semua boleh buat. Maybe you want 100% martensite, boleh buat. If you want 50% austenite, 50% martensite, how to do? We can do it. Okay, so just by the use of the TTT diagram. So I hope you get this in your brain. Okay, you are moving from phase diagram, which is under equilibrium. We are moving into TTT diagram, which is actually transformation of the phases at isothermal, meaning constant temperature. Time is the essence. Alright, so berapa banyak microstructure? Kita ada austenite, kita ada pearlite, bainite, martensite. 4. Ada lagi yang tak tunjuk kat dalam ni, sphaerodite and tempered martensite. Alright, so kalau no question, tak ada question, I hope you are still at the end there. Okay, now just to show you and also to let me go back, yeah. This particular TTT diagram, yeah, is only for specific system at specific composition. All right. For our phase diagram, you can see a whole lot of composition. But for TTT, this is only good for particular system. For this case is iron carbon, and it is for particular composition. 0.76 weight % carbon, which is reflecting the eutectoid composition. So C, E happening at T, E. Kalau you lose that point, you lose everything. Okay, so I'm not going to repeat that. Okay, now to continue on, just to look at the microstructure development, how we use this diagram. Yeah? So looking at the top part of your TTT diagram, let's say you start with a higher temperature, you need to work above 727 in order to get a stable austenite. So let's say you start somewhere up there. And then you cool, you drop your temperature, you cool to 620 degrees, let's say. Okay, and then once you get to that temperature, you said you maintain that temperature for a long time. All right, and then what happened at this point? Initially, you are austenite, 100% austenite, because this is just the beginning, the start point of the transformation. Once you cross that green line horizontally, you get to the dash line. What happened is that now you start to get pearlite, 50%. So kalau boleh show by area, 50% pearlite, 50% austenite. If you maintain that for a longer period until you reach the red line, you have converted all your austenite into pearlite, all laminating layers. Itulah yang berlaku. So this is the 0% pearlite line, this is 50%, this is 100% line. Easy, simple if you understand. Okay, all right. So you don't want to ask question, let's just move on. All right, this is to show you what happened to the TTT diagram if we move from the eutectoid composition. This is hyper-eutectoid, that means you are here. What happened? Hyper-eutectoid, you are the pro-eutectoid cementite. So the TT diagram is now looking a bit weird. There are an additional line to show that you have your pro-eutectoid cementite, CE cementite. So tak apalah, I am not going to deal a lot with this as long as you understand the eutectoid punya TTT and know that it is all specific to certain composition. Different composition will need for a different TTT diagram. Tak sama. Okay? Good. All right. Now, just quickly just go through apa the non-equilibrium transformation product tadi. Okay, so just now we call bainite kan. So bainite, they are looking like strips, okay, with long rods of cementite. Okay, this is diffusion control because it needs time in order to form that microstructure. Okay, so bainite dekat mana? Bainite, you need to drop your temperature below that 540 and then you just maintain your temperature so long enough, you cross the red line, you're gonna have 100% bainite. So this is one of the heat treatment that you can do in order to convert your austenite jadi bainite. Okay. So what happened? This is your bainite. Yang macam needle light ni, this is bainite. If you look internally, the micro constituent of the needle ni, of the bainite, is still alpha and cementite. Tak lari pada itu. The composition is still alpha and cementite. Cuma the microstructure looking like a plate. Right? So kalau you look for the next one, this is spheroidite. Spheroidite, we don't show it in the TTT diagram because it's still not tak stable. Memang tak nampak kat dalam tu. Spheroidite looking like this. Nama pun sparrow kan. Sparrow means like sphere. So they are on rounds. Okay. But inside this, okay, this round things is actually cementite and the background is ferrite. So you still don't run away from alpha and cementite. Alright? Everything is alpha and cementite. Rupa bentuk sahaja lain, microstructure tu rupa dia lain. Ada yang rupa plate, ada yang rupa needles, ada yang rupa spheroidite, spheres, particles. Right? So don't confuse yourself. If you get that, that means you understand it well. How do you get spheroidite? Apa pula teknik yang we must use in order to get spheroidite? You must start with a perlite or bainite. Okay, bukan austenite. You must have perlite or bainite, and then you can heat it and leave it at a temperature below eutectoid temperature for long times, 17 to 24 hours. Alright, then only, so that means you dah form your perlite, you dah form your bainite, and then you kata you naik balik. You panaskan dia balik, you heat it up again, alright, to temperature below the eutectoid. You panaskan dia balik in this region, maybe, okay, for a long time, then you're gonna get spheroidite. So it cannot be shown on the diagram here. But this is how you form spheroidite. Okay. So that composition, as I said, is still the same alpha and cementite. Tapi a good property of spheroidite ni is soft, right? Mana dia tulis ada tak soft? Dia tak cakap soft. Okay, shape is changing, reduce interfacial, perlite for a long time. Nanti somewhere dia akan cakap the property of spheroidite is actually soft. Jadi dia ductile, right? So that's the property of it. This is martensite. Look sebut martensite kan? How does it look like? This is how it looks like. They are in the forms of needles. Needle tu what? The black ones are the needles. It is cementite. The background is the alpha. You see, still alpha and cementite. Cuma now rupa bentuk dia lain. Wajahnya lain. Alright, the appearance is different. Martensite, actually, it is conversion from austenite, FCC, to BCT, body-centered tetragonal. This is the crystalline structure, changing from FCC to BCT. It is involving single atom jump alone, right? So you can just imagine je lah, the atom lompat keluar daripada position of the face-centered apa semua, and then they form BCT. So it doesn't require any diffusion because it's just jumping. All right. So it is not depending on diffusion. It is rapid. Okay. Depends only on temperature. And this is the temperature. All right. Okay. So that's martensite. Property dia, it is sangat keras. It is very hard. The strength is high and so forth. Right. So too much of martensite will not be good also because it becomes brittle. Okay. Alright. So ini apa? Sekejap. Let me. Alright. So kalau kita boleh get back our notion about this transformation from gamma austenite, if we slow cool it, we're gonna have alpha and cementite in terms of perlite, alpha BCC, and then if we quench it quickly, we will get martensite. BCT structure. And then we can temper it pula. Temper ni apa pula? Temper means you reheat. Tu sahaja. Reheat tapi below the eutectoid temperature. Okay. Reheat for a certain time, so you're gonna remove some of the hardness of that martensite, and then you create more ductile microstructure, right? That's why we do tempering. Then once you temper, we call it tempered martensite. Okay. All right. So nihan BCT, fused slip planes, hard and brittle. Okay, that's the property of martensite. Okay. Let's go to an example. Let me check if you have any question for me. Tak ada apa question, so must be crystal clear. Alright. So kalau ada question, just drop that. Okay. This is the example for you, alright, on the learning outcome number 3 just now. Be able to design a heat treatment in order to produce certain types of microstructure. So if you look at this TT diagram, it has this additional line. That means this is not eutectoid transformation. Okay, the composition is not eutectoid, 0.45. Okay, and now they want you to give the heat treatment. How are we supposed to design the heat treatment to produce 50% fine pearlite and 50% bainite? So kalau you look into this, the pearlite is on top region and the bainite is below, right? So how do I do if I want 50% fine pearlite? Senang je lah kot. Right, 50%, that means you always have to start above eutectoid, yeah? Because you have to start with austenite. Without austenite, nothing will change. Yeah? Now you will not get pearlite, you will not get bainite, you will not get martensite. Your starting point is austenite. Please know that. Alright, so you start from above T eutectoid, then you reduce your temperature, you cool to 600. Contoh kat sini is 600, you can go to 650, you can go to 680, you can go to 700, it doesn't matter. Alright, as long as you are within the pearlite punya region lah. So now it only says, shows here is 600, and then you hold your temperature, you gonna cakap lah how long you're gonna hold it based on the x-axis. Hold it until you get to the middle point. That says that 50% of your austenite, whatever austenite you have, 100% lah kan, 100% austenite, 50% has changed into pearlite. Alright, so you kena stop kat situ when you touch your dotted line, and then you reduce your temperature. Remember, at this point, at that point, you're gonna have 50% pearlite. What's the remaining 50%? Boleh bagi jawapan. What is the remaining of 50%? 50% pearlite, 50% ialah austenite, because you started with austenite kan, 100%, but then you reach to the midpoint. So 50% converted into pearlite because this is pearlite punya region. So in order to get 50% bainite, you just have to drop the temperature, drop to the region of the bainite, and then you just trace your point back to 0 time lah. This is turning back to 0 time, tak ada apa, there's no significance to that. So you start back from 0 time, and then you hold that temperature. If you stop in the middle here, only 50% out of your 50% austenite will change into bainite. So you don't stop here, you have to cross the red line so that 100% of your 50% austenite will change into bainite. Faham tak? And then once you have crossed that red line, you can stop there, you can stop here, doesn't matter where you stop, as long as you have crossed the red line, and then you have to quench to room temperature. So then you're gonna get 50% dekat sini, you're gonna get 50% pearlite, 50% bainite. Itu saja. Ada soalan? Anybody not clear, you better ask. Tak ada. Okay, you are not typing, that means you are good. Okay. Okay, type. Tak apa. You ask me because if you ask, then you clarify, then you understand, right? So I can see users are rising to 85. I hope you can just sign in your apps lah. Okay, your Power Apps to record your attendance, your final attendance for the semester. Okay. Apa soalan? Tak nampak soalan. Faham. Okay, good. Faham. Alright. Can I explain it? Okay. Okay, listen. Okay. How do you get 50% fine pay light? Oh, dia ada cakap fine Okay, fine pay light and 50% by night. If I want fine pay light, I better remain in the peer light punya region. So this is the peer light punya region lah between those two horizontal line ini dengan yang ini. Alright, so I have to remain there. If I want fine, I have to remain below. I have to remain temperature yang lower. If I go upper punya temperature, I'll be coarse. So that's why dia letak kat sini very low, dekat almost 600 there. Right, and then drop your temperature from the higher austenite temperature statement to, and then go down, drop your temperature until you reach about 600, because that is where your fine pay light will gonna timbul, will surface up, and then maintain that temperature until you reach to the middle point. Middle point says you're gonna convert 50% of whatever austenite that you have into fine pay light. Alright, so stop there lah sebab that's what you want, 50% fine pay light. Alright, and the remaining, because you start 100% austenite. When you reach to the middle point here, this is 50% punya conversion line. Therefore, you have reduced 50% austenite, dah jadi 50% fine pay light. Just because you hold it for certain time at that temperature and you touch the dotted line. Okay, then you drop your temperature, just drop, tunjuk je dia drop, okay, vertical line, and then reverse in terms of time, patah balik belakang in terms of time, because we want to start from zero balik, zero time. Okay, so ini balik zero lah, about zero lah, tu boleh lah nak tunjuk sampai ke ujung sini, no problem. Alright, so you reverse in time, and then this temperature is already in the bi-night punya region. Alright, so I'm good. Okay, so what I do, I just maintain my temperature. Remember, I have 50% austenite, my fine pay light will not change anymore because itu dah stable. Okay, only austenite will change into bi-night. So if I maintain my temperature, I reach to this point, 50% of my austenite will form bi-night. 50% of my austenite will form bi-night. Tapi saya ada 50% austenite. If it is 50% out of 50%, that's only 25%. Therefore, I have to maintain that temperature a bit longer until I touch the red line. Then I have crossed that 100%. That means 100% austenite that I have will change into bi-night. So 100% austenite tu apa? 50% tadilah, because you only have 50%. So this 50%, 100% change jadi bi-night. So now you have 50% fine pay light and 50% bi-night at this point. So just quench it to room temperature, so make everything stable. Alright, so that's how you do it. That's the line. Boleh I hope that's okay. Okay, let's look at 100% martensite. Senang dia, martensite senang. Kat mana dia tunjuk martensite? Okay, sini. Alright, martensite. You know, martensite only depends on temperature. Tak payah cakap lah berapa lama nak pegang hole, berapa lama, tak payah. Alright, martensite 100%, you must start from austenite. Still you need to start from austenite. So you drop your temperature from higher above, and then you drop your temperature, and make sure when you drop your temperature, ni salah label ya. Martensite ni 100% is this right? So you drop your temperature, do not touch the nose of this curve. Once you touch the nose, memang kita panggil ni nose, bukan saya panggil-panggil saja, memang engineers panggil dia nose. Don't touch the nose, don't touch any part of the curve. Kalau you touch any part of the curve when you drop down your temperature, that means you're going to form into perlite atau bainite. So don't touch them. Alright, you must keep away from the curve. Okay, so you drop your temperature from higher up, straight line goes down here. That means you're going to have 100% martensite. Habis cerita. Alright, because martensite form from austenite. So you drop your temperature, you tak langgar on this curve, so tak ada apa nak bentuk, perlite tak bentuk, bainite pun tak bentuk. Okay, hanya martensite because you dah cross the temperature where martensite starts to form. So kalau sampai bawah sini, you're gonna form 100% martensite. Kacang kan? Senang kan? Kalau faham, kalau ikut dan dengar cakap saya memang jadi senang. Kalau you tak dengar, you hilang kat ujung sana, memang you tak faham. Alright, so next, kalau ada soalan just leave it there, nanti saya tengok. The part C, ini part B ini salah ini B, ini C. Dah ni dia jadi D pula okay, dia ada buang lah tu. So ini C. C 50% martensite, 50% austenite. Macam mana nak buat? Okay, so 50% martensite maknanya when I drop my temperature, janganlah drop sampai room temperature. You drop to this point only. Point where 50% martensite form. That is the temperature at which 50% martensite will form. Stop there and then you maintain je lah. You kena maintain forever because you nak 50% austenite. Once you drop down to the room temperature, you're gonna form 100% martensite. So you kena drop down to 50% and then maintain the temperature forever. If you want 50% martensite, 50% austenite. That's it. Alright, so I hope that just makes sense. In real life, how we want to lower the temperature without langgar the node? You can do that by having proper cooling, quenching medium. Okay, kita ada different quenching medium. Let me go back. Okay, good question. I mean, you are already thinking like an engineer. Very well. Quenching medium. Dia ada different medium. Ada yang guna air, udara Ada yang guna water, air. Ada yang guna oil. So macam-macam. Alright, ada different cooling medium. So kalau water is the fastest, so you will avoid because memang boleh buat cepat. Dalam masa 1 second boleh buat. Okay, it can be done. Okay, alright, good question from you. Pukul berapa ya? Okay, dah 1:05. Okay, okay. Ya, buat fast cooling, betul tu. Alright, okay. So kita ada sikit sahaja lagi kita nak cakap pasal mechanical properties. Tadi pun dah sebut pasal mechanical properties, but kita always relate microstructure dengan mechanical properties. Right? So over here you can see the effect of weight percentage of carbon. The more carbon that you have, okay, what happen? Your tensile strength and yield strength increases. Okay, they are all in the same direction. Tensile strength, yield strength, and hardness. Kalau in terms of elongation, you know it is the opposite of all this strength, right? So that's what happened. Kita dah cakap pasal benda ni, we know that. And now what we do, we want to compare the mechanical properties of the different microstructures. We have fine perlite, we have coarse perlite, we have sphaerolite. How do they rate? How do they compare from one another in terms of mechanical properties? So you can see here in terms of hardness, okay, fine perlite will be the hardest among the three. Coarse perlite is the harder and sphaerolite is the softest among the three. Right, and you can expect in terms of their ductility would be the opposite direction. Spherulite will have the highest ductility because it's soft, and then followed by coarse perlite, and then fine perlite. Okay, so you have everything in the plot. So you can see the effect, the influence of amount of carbon. The more carbon you have, the higher the hardness and the lower the ductility. Good, right? So mudah sahaja. Now, if you compare, tadi kata fine perlite is the hardest, the most strong. Okay, how is it compared to martensite? MashaAllah, very far difference, very big difference between martensite and fine perlite. So martensite is super hard, okay, compared to fine perlite. That's why if you got too much martensite, you're gonna cause the material to be brittle. Okay, so not so good. Okay, jadi then what we do, we temper it. So you have heard about tempered glass kan, where it becomes stronger lah. Yang itu glass tu different lah, is ceramic. Now we talk about tempering martensite, whereby you reduce the brittleness of the martensite, you reduce the internal stress by quenching, because you quench dia kan. So ada banyak internal stress, and this is how your martensite has changed into tempered martensite. Dah tak ada needle, dia dah jadi more like elongated spherical tu kan, dia jadi particles like this. Alright, so now the property depends pula on the tempering temperature. So if you temper it at higher temperature, 600, below eutectoid temperature, alright, what happened? Tensile strength pun reduce, yield strength pun reduce, your reduction of area or ductility increases. That's what happened during tempering. Subhanallah, all these things, engineers are, having the knowledge how to change the properties of the materials. Okay, so this is actually a summary of everything that we discovered into this lecture. We convert austenite actually into perlite, right? If we do slow cooling, we can get perlite. If we do rapid cooling or quenching, we're going to form martensite, and upon moderate cooling, we can form bainite. So the microstructure, platelet, needles, they are different. And if you reheat martensite, you're going to have tempered martensite. And in terms of strength and ductility, it follows this general trend. Okay, you start with spherulite at the bottom, having the most ductility and the least strength, and then you move up the ladder to coarse perlite, to fine perlite, and bainite in between martensite and perlite, and then you have martensite, the highest strength. All right, so that wraps it up nicely. So we are done for phase transformation. Okay, so any question? Okay, I'm just glad, alhamdulillah, we have finished discovering about materials from chapter 3, talking about crystalline structures, and then we move into crystalline is perfect structures, and then we move into defects, and then we talk about diffusion, how atoms move, and then we talk about mechanical properties, about dislocation, and then we talk about phase diagram, and today phase transformation. All right, so I hope you can appreciate the knowledge in material science, and I'm sure you will use, if not all, some of the information in your future classes and in your future career. All right, so that's all from me, and I wish to jom buka video cam. We need to take a picture. You also can take a picture because saya mungkin tak berapa pandai nak ambil picture semua tu. So let's go live. Show your faces. It's the end of the semester. Let's see, how many are still there. All right. Anyone want to turn on your webcam? Let's have many people on the webcam. No? Nobody want to show your face? Malu konon. Yes, there you go. Yeah, these are all my good students. Yeah, my strong supporters. All right, now I can see you. Tak pernah kenal macam mana rupa Amir Fitri. One Amir Afiq. Okay, hi. All right, good, excellent. So maybe kita boleh tutup ni. Yeah, more to see, more on board. Let's have more on board. Okay, hello, nice to see you. Dah last week dah. Where are my girls? Tak ada girls ke? Ya, malu semua girls. Hi meow meow. Right. Okay, webcam rosak pula Azfar. Okay, let's see more. Okay. Dr. Azwan tak ada hari ni. He's busy marking your exam. Busy marking your project. Alright, so I'm alone today. Okay, ada lagi want to show your faces as just to record, put history. Right. So how do I do it? I just take dia punya print screen. So see. Webcam rosak. Okay, any more? Let's have many more. It would be fantastic to have everybody. Okay, let's try. You guys, in case saya tak berjaya, you guys better ambil. How do I do it? Sekejap. Try. Yeah, just take screenshot kan. Okay. All right. So I wish to thank everyone, although I miss you, not seeing you in person, not to see your face more often. Hopefully our path will cross again. I wish you all the best for your future endeavors, in your future courses, and especially in your EA. We are still working on your coursework. I hope to share with you on your coursework marks, all right? And then hopefully you can actually really work hard for your EA. EA is 40%. So jangan waste that, okay? Even though now maybe you kata coursework you're not so good, I hope you can work towards your EA. You have 24 hours to answer to the fullest. I don't mind you sharing your discussion before nak jawab. You can talk to your friend, you can talk to whoever you nak Google, do it. As long as at the end of the day, you write your own original answer. Don't let me find any key questions that I need to answer that. Okay, sikit saja. We are still working on your coursework. I hope to share on your thing. Okay, let me and especially in your EA. We are still working on your coursework. I hope to share. I hope you have enjoyed the course. All right, you're supposed to appreciate the course and. Minta maaf, I seek your apology. I seek apology for any wrongdoing. Langsung tak ada girls tau. I don't see my girls here on the. Warahmatullahi ta'ala wabarakatuh. See you around. Okay.